Hey everyone, it's Dr. Calkins, and we're doing one of our last major busy labs that do not require gloves, goggles, aprons, closed-toed shoes in lab, and that's experiment 20. Experiment 20 is called Houston, we have a significant problem because we're dealing with significant figures. And significant figures are numbers that we use in science because they have meaning. So a couple rules to follow as we get to our first section, and what's nice about this particular lab is it walks through our lecture step by step by step and shows us each of the important ideas of our class. So non-zero numbers are always significant. That just means if you're not a zero, you're important. If you're written in a scientific research journal, textbook, whatever. If you're a zero that happens to be stuck, like this one, between non-zero numbers, you're significant by default. So then we have to worry about zeros that are even more unique, and these are the ones students tend to have trouble with. If you're a zero that shows certainty, we call those trailing zeros. Those are significant. So here, if you're buying 120 liters of whatever, gasoline, who knows? Notice this zero goes beyond the numbers. Because you go beyond, that's showing more exactness, more certainty. Those are the ones we want. So notice these are going past the number. The ones we want to watch out for are the ones that show size. These are called leading zeros, and they're leading you to the decimal point. They're not important. Those would be the ones we would remove if we were to go to scientific notation. So in Avogadro's number here, notice all these zeros just lead you to the imaginary decimal that's not even shown. So right there. In this situation here with a very small number, we're going all the way back. Here we're going all the way back, so it doesn't matter which side we're on, we're going to the decimal, not away from it. Be careful if you have a decimal point, those are important, because they're showing that that zero happens to be a zero, but otherwise it would be unimportant. So if you see that decimal, or if you see something underlined, those are the exceptions to that leading zero kind of rule. The only way to get good at anything is to practice, and that's what we're doing on the next page. So the first thing we're going to do is practice significant figure numbers. So who has trailing zeros, who has placeholding zeros, because those are the ones that students have the most trouble with. So notice up here with 52.010, we have a zero in the middle, but we also have the zero that is going away from our other numbers. So we would call it a trailing zero. It's not showing the place of the decimal, it's showing you beyond, showing you exactness. So here we have the 5, the 2, the 0, the 1, 0, so all 5 are significant figures. This next one, we do have zeros that are showing you to the decimal. Those are the ones we want to watch out for. So we don't have any trailing. Trailing zeros would be over here. So we don't have any of those. So not applicable. And then over here, we do have the 3 zeros to the decimal, the one in front. So there are 4 that don't really matter to us, just showing size. So the ones that do matter are the 3, the 7, and the 8. So take a few minutes to try some of the next ones. Just pay attention to where those zeros are and if they're leading you to a decimal or if they're leading you away, in this case trailing away from the rest of the number, showing exactness. So one step further in our understanding of numbers, we need to do scientific notation. And this is using significant figures to do scientific notation. So here we have zeros that are kind of stuck in between. Those are going to be important by default. This one is going away. So notice that's one that we keep in our scientific notation. As we put it in scientific notation, we need to move right or left. So this is a big number. We're going to move left 1 space, hence only positive 1 power. That's a large number. In the situation here, we have numbers that are not useful. So we're going to get rid of those by putting it in scientific notation by going 1, 2, 3, 4 spaces. And that would give us 3.78 times 10, because this is a small number, we went to the right, that's a negative 4. And again, small number, much, much smaller than 1. So try that by going left to right, moving, remember big numbers, positive exponents, little numbers, negative exponents as you check your work. So on this page, we're using significant figures to do math problems. So there's 2 rules to follow. Addition, subtraction, you're going to go by the fewest decimal places, so the answer that runs out first is going to be the actual place where we stop our answer in our calculator. But if we're multiplying and dividing, PIMDOS rules say those are most important in the end, and those go by fewest significant figures total. So we look at this one and we do it in our calculator, 4.56, 2.1. added together. Notice here is the tenths place, here is the hundredths place. So our answer, even in our calculator, might have something that's we want to circle in our answers, but because this number runs out in the tenths place, we have no idea what its hundredths place could have been. That tells us we use this number for rounding only, and this gives us one of only 2 errors I've found so far in my lab book. This should have been, instead of cut and pasted, this should have been 6.7. Over here we have the same kind of idea. We have 3 versus 2. So 3 sig figs versus 2 sig figs, 2 wins. So we want to keep 2, the rest just determine rounding, and that's why we keep 8.2. So as we subtract this next one, our calculator is going to give us 291.53. And if that's a choice in our homework, you might want to circle it because it's what your calculator shows you. The disadvantage of this particular number is this one had a hundredths place, this one has a thousandths place. We need to stay at the hundredths place, so this one was perfectly fine. Our calculator didn't lie to us. It went by fewest decimals just by default. Not by fewest sig figs, that's multiplication and division. As we try this next one, we have 3 sig figs versus 4. This is a 0 that shows you exactness, certainty. So 3 versus 4, we multiply those. We're going to want only 3. We want the fewest number. So if you multiply this, you get 4,920.43. That's what our calculator tells us. If you circle this answer, you're going to get that warm fuzzy feeling that it actually matches the homework, but it's going to be wrong because you have a lot more numbers than what we started with. So this has 6 numbers, 1, 2, 3, 4, 5, 6. We have 3, we have 4. We can't have an answer that fancy, that specific. So 3 versus 4, 3 wins. So we want the first 3. The zeros along for the ride, so 4,920. This 0 shows size, nothing more, so it's not an important one. The 3 significant figures that matter are those. We need the 0 because if you had a paycheck for $4,920, that 0 is important for size, but not for anything else in science. So take a few minutes to try the rest of this. Just remember PEMDAS rules as you're doing your mathematics. And again, this was fewest sig figs. We'll come back. In our metric ruler problems, we have our entire metric system. What's unfortunate for us is in the 1970s, I think it was President Ford that said we would adopt the metric system within 10 years, and we never did. So now we have to deal with the units for the rest of the world compared to our units, which is painful. Theirs is pretty nice because it's a power of 10. Notice here's our standard unit of meter, liter, grams, calories, seconds, hertz, bytes, everything else you see in cell phones and computers and so forth. Go up 3 powers of 10, so 1,000, you get to kilo, another 3 mega, giga, and tera. So you see a lot of those in electronics, in particular with sizes of files and storage and so forth. As you go smaller, we go by tens, so this is a tenth, a hundredth, and a thousandth, so we get to that milli. Micro, you see that in microbiology. We saw that with microwaves back early in the semester, so that's 10 to the negative 6. So a millionth, and then we have a billionth, and then a trillionth. So we go from a trillionth all the way to a trillion using the metric ruler. What's nice about these rulers is you don't have to use a calculator if you just plug the number in and then add or take away zeros to find the new conversion. So let's try that on the next page. So notice here we have 2.54 kilometers. So 2.54 kilometers. And notice we put the 2.54, that decimal is on the right side of kilo because we're in a kilometer as a unit. They want us to go to centimeters, so we just keep adding zeros, and then we move our decimal from here over to there, and we get 254,000. So this is the fastest way to convert in the metric system without a calculator. As we look at this one, we have 0.0891 microliters. So here's our decimal, 0.0891 microliters. They want us to go to liters, so we add zeros to get to liters, so the decimal moves from here over to here, and now we have this teeny tiny number, 8.91 times 10 to the negative 8 liters. So let's do that for an example and let you try some more, but this is the fastest way to do a metric conversion, and you get to use one of these charts on your exam 5. So here we have 350 So 34.3 millimeters, trying to give away the answer. So if we have that, we need to find our decimal. So this is milli, so here's our decimal on that right side corner. In front of that number we have 34, so there's 34 milli and 0.3. So that's how we put the number in. We have our decimal on the right side column, or edge, for the unit itself. Now they say, what if we want to go to kilometer? Well, kilometer means we're going to have to move this decimal all the way to over here. So for us, that just means add zeros and move the decimal here from here. So the answer now would be, we got 1 0 in front, 1 2 3 4, 1 2 3 4 in between our number, and then a 3 4 and a 3. Put it in scientific notation means move it back -1, -2, -3, -4, -5. So 3.43 times 10 to the -5 kilometers. So try that approach on the rest of this page, and that'll give you a lot of practice with the metric system. All right, as we move to page 138, we're going to use measurements, but remember we're going to use values between the markings. So we're going to make sure we have as much significance as allowed by our measuring device, in this case a ruler. As we go to the bottom of the page, and I'll do this for you. You can do this at home if you want, but because they use different printings of these papers, they're not always exact. So as we measure this one, we're going to be in that 15 and some change kind of idea. So notice it shows 15.1, 15.2, 15.3 roughly. And if we go to the middle of that, it's not quite to 15.4. So somewhere in there is going to be the answer. For purposes of our lab book, we're just going to use 15.40. But in reality, for this photocopied print-off, if we were to zoom in, it's really about 15.2, almost 3. So in reality, it's about 15.27, 28, 29, somewhere in there, because we're using between the markings, not just the markings, and that's what significant figures have to do with measurements. Let's do the other side real quick. So measuring from here down to there, we're about 4.5, 0.6, 0.7. That's almost right in the middle, so it's about 4.70. For purposes of the lab book, we're going to run with 4.77, and that's just because that's what you'll see later, but definitely it wasn't quite to that marking. To get area, you would multiply these. Just remember you have 4 versus 3. If you weren't using your ruler to its full capability, you probably have 3 versus 2, and we couldn't get a good as answer. When you do that, you get 73.5 because it's 4 versus 3 sig figs, 3 wins, and centimeters times centimeters is centimeters squared. As we go to the next page, we do the exact same thing, but with a cube. You don't have one of those at home, but I have one here. So we're going to measure our cube. So we have one measurement here at almost perfectly 5. If you wanted to use 5.00, that's fine. In our lab book, for purposes of the answers you're going to see later, that's 5.05. It's almost perfect left to right, so if we rotate it, here we have just right in front of 5. So for purpose of our lab book, we use 4.99. Notice we're going between the markings, and then we have the skinny edge, and we measure it, and you're getting somewhere around 3.7-ish for this one, and they're using 3.74 in the lab book. So this is volume, so we need length times width times thickness. 3 versus 3 versus 3 should give us an answer in 3, and when we do that we get 94.2 for our volume. That volume is going to be used lower on the page, so bring that one down. We have 94.2 for our volume. If we go to the balance and measure this, we're going to get 40.066. Density is mass per unit of volume, so you put 40.066 grams on top, 94.2 centimeters cubed on bottom. We have 5 versus 3, our answer needs to be in 3, so we get 0.425. Would our wooden block float or sink in water? Water has a density of 1.00 grams per centimeter cubed. This is a lighter density, so wood typically floats on water, and this is why. As we move to the next page, we're going to see temperature. And what's important about temperature is where the charts are related. So freezing for water, for Fahrenheit is 32, boiling is 212, Celsius 0, Celsius 100 for its boiling point, 273, 373. So notice these are just offset by 273. That's these formulas here. So those are the easiest ones to do, adding and subtracting 273. For the other ones, they get a little messy. Just remember that if you have Celsius, you need to cancel Celsius, and then you get Fahrenheit, then you can add Fahrenheit. If you're in Fahrenheit, you have to subtract Fahrenheit first so that those cancel, and then you get Celsius. That unit conversion is a big portion of our particular exam coming up. So let's do a temperature conversion for practice. I'm going to jump down to the second one just to show you something unique about the temperature scales themselves. So here for -40, if we're going to go to Kelvin, notice we have Celsius. We want to go to Kelvin, we're going to add 273. So if you add 273, you're going to equal 233 Kelvin. It's not so bad. Those are definitely the nice ones. But if we go the other direction, we're going to have to take Celsius to Fahrenheit. So that's this one up here. So if we plug in -40 Celsius, we're going to divide by 100, multiply by 180, hit equals, and then add 32. So in our calculator, we need this to happen first through PEMDAS before we do any addition. So take -40, and this is a 9/5 that you'll see in some textbooks, but 180 over 100 is fine too. That's the difference between Fahrenheit and Celsius freezing points, boiling points. And what you're actually going to get here is -40. So eventually, the temperature scales have to cross. And this is the magic number at which Fahrenheit and Celsius kind of touch streams before they keep going to colder temperatures. So pretty unique, and that's also a true and false question in the homework. So take a few minutes to use these formulas and to plug in those temperatures now. All right, we're on the home stretch with some major problems using multi-step situations, this one with energy. So heat is measured in calories typically, or joules. Joules is more for physics kinds of things. Specific heat is a value that represents how much energy is required to raise 1 gram, 1 degree Celsius. Water the standard at just 1 calorie per gram per degree Celsius. Lots of metals are very low because it doesn't take metals very many calories to heat up 1 gram, 1 degree Celsius. So it's important that water is so high. That way the oceans warm up very slow and they cool down very slow, keeping our planet moderately stable. As we look at our Q kind of thing we showed you in the homework, this looks like a triangle. Q equals mass times specific heat times delta T. We're looking for Q, so if you cover up Q, it's really just multiplying those three together. And that's our cute way of avoiding algebra. So our problem is number 4. That's the one we're going to work through together. Using the Q triangle, we need to figure out how much heat does it take to boil 1 cup of coffee. So if 1 cup is 237 milliliters, we need to convert that to something that we can use, in our case, grams. So here's our conversions. We just need to orient them so that units cancel. So if we have 1 cup of coffee, we need cup to cancel. And we were told that 1 cup is 237 milliliters in volume. Cups cancel. We want to go to grams, so we need milliliters to cancel. Milliliters cancel by being in the numerator and the denominator. And notice we have 1 gram per 1 milliliter. So we multiply 1 times 237 times 1 divided by 1 divided by 1 doesn't really change anything at all. We get 237 grams of water. And that's our, Now we need our specific heat, but this is water. So there's our specific heat. We need our change in temperature. Our temperature was room temperature 21, it boiled at 100. So in that situation, we're going to take change in temperature, which was the final temperature of 100, and subtract the initial room temperature value of only 21. This will give us 79 degrees change. Notice we're in the ones place, so we stay in the ones place, and that one will be our last value needed to go here. So to solve, we need the mass times the specific heat times the change in temperature. So Q equals the mass. We found that to be 237 grams of water. The specific heat of water is 1 calorie of water per gram of water times degrees Celsius of the water, so grams cancel. And then we have 79 degrees, which is the temperature change, and Celsius cancels. Multiply 237 by 1 doesn't do anything but waste time, but then changing units, we multiply by 79. Gives us an answer of 18,723 calories. You want to circle this answer in your homework because it looks pretty and it took all that work to get it. You circle it and it's still wrong. Why? Well, we have 3 sig figs, 3 sig figs, 2 sig figs. The answer that we circled had 5. That's never going to work. 3 versus 2, 2 wins. When you do multiplication and division, that's fewest significant figures from our previous page. We want 2. Everything else is rounding. So it's really just 19,000 calories given the exactness of other numbers. So this is what we want. So be careful when you do calculations like that. Something very similar we're going to do, compare ourselves to a superhero, and then we're just about done. So the first thing we're going to do here is compare ourselves to an ant, just like Ant-Man on the Marvel movies. If we were made of ants, how many ants, if we stack them nose to butt, would we be tall? So how many ants tall are we? So I'm going to use my height. You can use your height, doesn't really matter. You can use mine if you want. That's what it's going to be in the answer key. But if you want to use yours for fun, that's perfectly fine as well. So I am 6 foot 3.5 inches in height. In order to do our conversion to ants, we're going to have to get to total inches of height. So for 6 feet or for 5 feet for most students, maybe, if you're 6 feet, you need to cancel feet. Recognize that there's 1 foot and 12 inches. Feet cancel. And then you have 6 times 12, which gives 72 inches, plus the extra 3.5 inches in height. For me, is going to be 75.50 inches. So as exact as you know your height, you can use that to give you more significant figures. Because we're measuring ants in millimeters, we need to convert our inches height to millimeters. The only way to do that is to go through centimeters. So that's going to be a multi-step conversion process. So we're going to take this number. We're not going to worry about significant figures yet because it really only matters in the answer. Just like in all math classes, you don't want to round too early and too often. So we're going to bring this number down, 75.50 inches. We're going to get rid of inches by putting it on the bottom. We're going to look for our conversion. 1 inch is 2.54 centimeters, so 1 inch is 2.54 centimeters. Centimeters is not millimeters, so we need to convert again. Centimeters to millimeters. If you look on your metric table from earlier, you're going to realize pretty quickly that 1 centimeter is 10 millimeters. So as we multiply 75.5 times 2.54 times 10, the ones don't matter, we get a much larger value of 1,917.7 millimeters for me. Or if you were to go to Canada or Mexico, it would be 1.9 meters roughly in height. Lastly, 1 ant is every 6 millimeters. We know the total. So if every ant is 6 millimeters, we just need to take our number, convert it to ants. So 1,917.7 millimeters total height for me. Get rid of millimeters. And this process is so common over the next several chapters, that's why we practice. This is just a completely random example of unit cancellation. We know that every 6 millimeters is 1 ant. So take our number, divide by 6, and we're going to get, for me, 319.6166 ants and some change in our calculator. Obviously this is way too complex of an answer. What we were limited to in the very beginning was some numbers like 3 sig figs, like 3 sig figs. So we need 3 sig figs, so keep those 3. Use this one for rounding. So I'm going to say 320, but that 0 needs to count, so either underline it or put a decimal. But 320 for me. And you can do this for yourself, and I'll give you that time now if you want. So using our superhero analogy, if we're made of ants, then we should have the same capability of ants, which is to pick up 20 times their own weight. So let's calculate that given our weight. If you want to pretend that you're the weight you were in high school or as a baby, nobody cares. Nobody's going to judge you over the internet. I'm going to use my weight. If you want to use mine, that's fine. Completely up to you. 235 pounds. So that's 3 sig figs. In our situation here, we need to convert to grams. That's going to be pretty intimidating because grams are tiny. Those are paper clips. To get closer, we're going to have to take our pounds and get rid of them. Not through exercise, but through math and cancellation. So here we have 1 pound is 454 grams. So this is 1, and the top is 454. So multiply, you get a gigantic number, 106,690 grams. So pretty intimidating number. Hopefully yours is less than mine. Now we need to go to ants. If ants are only 0.004 for those wood ants that crawl around on trees, then how many ants in weight would we be? So we take our value down, 106,690 grams. We get rid of grams by putting them on the bottom. Here it says 0.00400. That's 3 sig figs with 1 ant. And again, we're not going to worry about significant figures yet because we don't want to round too early too often. We get 26,672,500 ants. If each one of those ants collectively can pick up 20 times their mass, that's what we're going to pretend as superhero. So we're going to bring this number down. So 26,672,500 ants. Get rid of ants. Not through poison, but through cancellation. Cancel. We know from above that one ant strength is 20 times its mass. So that's done for you already. So 1 ant would be 0.00800 grams. That's 3 sig figs. We want to convert that to tons because that's more meaningful for cars we're going to throw around in a superhero movie. So get rid of grams. And 1 pound. There is 454 grams. Get rid of pounds. So pounds there, we have 2,000 pounds and 1 ton. So tons should be left. Calculate this, you get 2.35 tons for me. 2.53 tons is, if cars weigh about 1/2 ton, that's almost 5 little cars that I can throw around if I were a superhero, but I'm not. 2.35 is the answer. So as you finish this lab, you're going to notice there's a lot of practice on the remaining pages. This will be a take-home quiz that you'll deal with later. So as you work through these 15 problems and these 15 problems, use a lot of the ideas that we practice on to survive them, worrying about significant figures. The biggest issue with most of this homework is notice all the answers are pretty much the same. We're not so worried about you calculating the problem correctly. We're worried about you taking that number and making sure that it's in the right number of significant figures, either by fewest sig figs with multiplication and division, or by fewest decimal places with addition and subtraction. So enjoy the remaining of the work on your own.